Hello everyone, thanks for joining us today in this exclusive technical webinar, Advanced PCB Cooling Simulation with CST Studio Suite. We are very excited to have you here with us. In today's session, we will explore how to simulate electronic PCB cooling using the Conjugate Heat Transfer CHT solver in CST Studio Suite. You will learn how to predict thermal performance in complex PCB layouts and understand key modeling techniques that are essential for a successful thermal analysis. It's my pleasure to introduce our speaker, Dr. Daniel Ochoa. He is a senior technical sales engineer here at Bias 3D with more than 10 years of experience working on low frequency RF and microwave systems. He has extensive expertise in modeling and simulating electromagnetic problems, making him the perfect expert to guide us through today's topic. So, with that, let's get started. Daniel, the floor is yours.
Perfect. Thank you, Manuel, for the nice presentation. So, hello everyone. Thank you for joining today's session. So, as Manuel mentioned, the topic will be PCB cooling simulation with CST Studio Suite. Over the next, I will say 45 minutes, I will walk you through how to perform and optimize PCB cooling simulation. Okay, we will discuss mainly about the conjugate heat transfer solver, and we will talk about the multiphysics capabilities that we have in CST Studio Suite. Okay. So questions will be handled at the end of the presentation, so we will have a Q&A at the end. So let's begin with a short motivation. Well, it's a simple question actually. Why do we need thermal simulation of a PCB? And I mean, it's no surprise for anyone that as electronics become smaller and more powerful, managing the heat that they create is critical. Okay, so you have high power density that might lead to hot spots on your design, and that will degrade your performance and reliability of your device. Okay, basically using thermal simulation, we can predict any issues before even prototyping your design. Okay, and there is also the fact that there are multiple challenges when it comes to cooling a PCB. We're dealing with a very complex multi-layer stack-up. Basically, it's an isotropic material all the way on probably the Z direction, and we have limited space for to cool down the device. Basically, we have to put heat sinks, airflow, any other form of cooling technique, and we're working with a limited space to do that. Okay, and on top of that, you have three forms of heat transfer that they are interacting each other, and it's not a trivial interaction. Okay, so you have to model with accuracy all of this to get realistic results. That's why we use tools like this one, like CST Studio Suite, because of that multi-physics capability, and you will find there is a lot of value on using that before even creating the final design or prototyping your design. Okay. So I will briefly discuss some of the basics. Okay, you might know that we have three forms of heat transfer. Okay, so we have conduction, convection, and radiation. And no matter what we do, we will encounter those on everything that we do in our everyday life. We will encounter these three forms of heat transfer. Okay. In most electronics, which is the topic of today, the heat will start mostly as conduction. Okay. And it happens in the solid materials due to ohmic or dielectric losses. Okay, then that heat exits our structure either through convection to the surrounding air or through radiation at the surfaces. Okay, So all of these three forms of heat transfer, as I mentioned, they should be considered when we are doing a thermal simulation, okay? And it's very important to understand what's the mechanism that dominates this form of heat, so in our model, in our simulation model, because that will help us define the correct, let's say, boundary conditions and even the definition of our material properties. Okay. So let's dive in a little bit more on CST and what CST offers in terms of multiphysics capabilities. Okay. So in CST, as you probably know, we have a suite of tools, solvers, mesh technologies, however you wanna call it, and we do have a multiphysics module inside of CST Studio Suite. So in that multiphysics module, we have several solvers, okay, to tackle all of this form of heat transfer and even more. Okay, multiphysics not only refers to a thermal problem, you also have a mechanical or electromagnetic, everything combined. Okay, so we have the classical thermal solver that it supports steady state and transient simulations. And these two solvers, they use finite element method to solve thermal conduction inside all geometries and the background. And convection and radiation are approximated. And the way they do that is using thermal surface properties. Okay. And we also have the conjugate heat transfer, which is the main topic of today. And this solver is capable of handling conduction, convection, and radiation, the three forms of heat transfer, at the same time using computational fluid dynamics in one solve. Okay. So if you need accurate radiation and convection calculations, this is the solver that you should be using, the CHT. Okay. And we also have the structural mechanics. We will not discuss too much on this topic, but it's there. We simulate thermal stress. We can get deformation from the structure if needed. Okay, so all of these modules are they all share the same graphical user interface in CST. Okay, and the link between them is actually very easy to do. You can link all electromagnetic, not all, but you can link the electromagnetic solvers available in Micro Studio and Low Frequency or Particle Studio and even PCB Studio, which is also the topic of today. And that linking between all of these solvers is what enables the multiphysics simulation. Okay. So how this moving from one physics, let's say electromagnetic, to a thermal analysis works in CST. For that, we have to understand how this link happens. Okay, so the link mechanism is using field sources in CST. Okay, the field sources basically is a box that represents whatever is happening inside of your design. It could be electric magnetic fields, it could be losses on your device, which is the case, and it's very easy to design. So there are two ways that we can define these field sources when it comes to solving a thermal problem, electromagnetic and thermal coupling simulation. That is, you can do it manually, okay, or you can do it using the available workflow wizards on CST. Okay, the easiest way, of course, will be using the wizard. It's very easy to use. You just have to select what type of analysis you want to do, if it is unidirectional or bidirectional. And the system CST will handle the creation of the necessary field source and field monitors, so the loss is mapped between one physics to another, basically. Okay. If you do it manually, everything that CST is doing on the wizard, you can do it manually, of course, but it requires more steps, let's say. Okay. You will need to define your monitors, field monitors, so CST understand or use those field monitors to calculate the losses. Okay, and then you have to bring the field source using those losses. Okay, if you're doing bidirectional approach, You can also do it manually, but for that you have to bring a field source that contains the temperature as well. Okay, so keep that in mind. We will come back to this in a moment when we discuss how to apply this PCB simulation. Okay, so what do we have in CST? What technology we have to analyze thermal simulations? Okay, so CST provides, and this is not a comprehensive list, of course. CST provides advanced thermal simulation features like we have GPU support, we have EDA import if you want to bring your PCB design, complete PCB design. We can have flow resistant modeling. We also have compact thermal models in case you want to bring a chip to your design, to your simulation model. That's also possible. You can simulate altitude effects. This is taken, or it is considered when you add a fan to your system for cooling. Those altitude effects will be there, and you can use the thermal interface materials. You can even model a multi-fluid cooling system if you want to. Okay, and we will talk a little bit about that in a moment. Basically, the tool will help you build a realistic and efficient cooling simulation. Okay, all again in one single graphical user interface. So let's talk about the workflow, how it works exactly, and this is a case for a unidirectional approach, meaning that we are moving from one physics. So let's say we're moving from the electromagnetic problem to the thermal problem, okay? But we're not going back. Going back is a bidirectional approach, and it's also possible, okay, in CST. But of course, at some point, we will have to close this cycle or the workflow to make it bidirectional. Okay? So this is the case for a unidirectional approach when we do electromagnetic and thermal coupling. So we start by importing our PCB model, whether if you're using a CAD file or an EDA file. Okay. And we will see in a moment that if you bring that on an EDA file through PCB Studio, you have the option to simplify via the EDA import interface. You have the option to simplify that PCB for a thermal simulation. Okay. Then you have to select the solver technology. Select the appropriate solver technology. Again, we need to consider the heat, the three forms of heat transfer for that. Okay. You need to import your losses into your project. And of course, after that, you can modify your project if you want to. That means adding more heat sources, adding a cooling system for your design if needed. Then you have to select the mesh technology. So we have tetrahedral, hexahedral, and we also have an octri mesh technology available, which is the picture that you're seeing in step number 5. Okay. This is only available on the conjugate heat transfer solver. Okay. Of course, you need to define your boundary conditions. This is a very important step, and we will discuss that in a moment. And as optional, you can create your field monitors if you want to. Recommended, not needed, but recommended. And after that, set up your simulation parameters. That means you have to activate, in the case of the CHT solver, so would you like to analyze the three forms of heat transfer? Are you doing in a steady state, or are you doing a transient simulation? All of that is controlled directly on the setup of the solver. Okay. As I mentioned, the thermal solver is GPU compatible. So CHT, we can use a GPU to accelerate the simulation. Okay. So you have to activate that option in there. And after that, it's just running the simulation, checking the results, doing post-processing if needed, using any of the template post-processing that we have, and visualizing the results, either 1D, 2D, or 3D results. Okay. Those are the typical steps that we follow every time we want to create, we want to do a simulation, a coupling simulation between electromagnetic and thermal. Okay. Now, it is important, and it is important to understand that when we talk about losses, we are talking about DC and AC losses, okay? Unlike the other modules that you're seeing in here, so when we talk about high frequency, low frequency particle studio, well, not particle studio because this is losses on particles. So these two, normally we deal with AC losses, okay? But when it comes to PCB Studio, we are talking about DC losses, okay? And in the case of Particle Studio, the setup of that coupling, the thermal simulation, electromagnetic thermal simulation coupling, we have to do it manually at the moment, okay? So the wizard that we showed before is available if you're using any of these three modules. If you're using Particle Studio, you have to do some manual work, but it is not complicated. So I will show you how to do it in a moment, okay? So the way you go about doing that in PCB Studio is like this. So we use the solver IR drop to calculate the DC losses, okay? The only thing that you have to do is activate, in the setup of the solver, there's a specials tab in there. You have to go in there and activate under co-simulation, activate the export losses for thermal solver. That's the only thing that you have to do, okay? This way, CST will automatically calculate 3D losses in all traces and layers, okay? Those will move to the thermal problem as a field source, and we also calculate losses in all components that are part of the, let's say, the nets involved on that IR drop analysis, okay? So that's the only thing that we need to do to get the losses from the electromagnetic analysis and move it to the thermal braid. And now that we are talking about PCB Studio, let's continue on that topic. I will show you some of the key features that we have, and these features are available in PCB Studio and are exclusive to thermal analysis. So what you're seeing right now is available for you to, let's say, reduce the complexity of your PCB and make it easier for the tool to simulate a thermal problem. Okay? So the first thing is that you have options for EDA or import. I'm showing you a list here of options that you have available in CST Studio Suite. And also, there is the option to simplify your, to add simplification to your PCB. The simplification works like that. So you can have either no simplification, so everything will be there. You can do layer wise, so each layer is averaged separately in the problem, or you can use all materials. So you get only one single block representing that PCB, and in terms of material, CST will create an anisotropic material that average all the layers that you have in there. Okay, that, of course, depending on the complexity of your PCB, you can choose any of these three options. Okay, I will, if we have time at the end, I will do a demo and I will show you this too, so you can see the difference, what happens with my results when I use no simplification or when I use layer wise. Okay. Another interesting feature is that besides creating layer simplification, that simplification, you can mix simplification levels for certain areas. So for that, we use area restriction. In PCB Studio, you just have to select an area. That selected area will be imported in detail. Okay, so that's why you see the PCB traces, all the layers for that particular area will be there. All the traces, bias, everything will be there. The rest of the project will be simplified using layer-wise simplification scheme. Okay. And another interesting feature that we have is that you can set up directly from PCB Studio. You can create heat sources corresponding to the footprints of your components. Okay, so when you do the IR drop automatically will calculate losses on the components that are part of the nets involved in that IR drop. Okay? That's why you see a list in here with power, height. Those are calculated directly for the IR drop in this case. But you can select any other component, add it to the list, okay, and assign power and a certain height for that component in 3D. Okay, you can do it directly from here. You don't have to do it on the thermal environment. If let's say if you have a very populated PCB with many components, I think it would be easier to do it directly from here instead of doing it on the thermal project. Okay. Now, let's briefly discuss those were some of the key features specifically available in PCB Studio for thermal simulation. Okay. Now let's briefly discuss PCB cooling solutions available in CST. So the list that you see on your left, this is basically on the internet. If you search for common cooling solutions on the internet, you will see a list like this one. There are more available, of course. But what I find interesting is that all of this that I'm showing you here, which are the, let's say, the main cooling solutions that you will find, are available in CST. So either you use heat sinks, you can use fan, you can bring your fluids, multi-fluid, to your simulation environment, the heat pipe, thermoelectric cooler, all of that is available. And moreover, we also have tools like this one, toolbox. If you click here, something like this will pop up. And this is not only available for the conjugate heat transfer. Okay? This is also available for the classical thermal solvers that we saw before. So this toolbox will actually help you create, for example, a fan. If you want to do an axial fan or a centrifugal fan, you can do it. It will create a 3D model of that just by entering the physical dimensions, let's say. Okay, that is also part of CST. So the screenshots that I'm showing you here in this picture are coming directly from CST. That's available for cooling down, let's say, your simulation model. Okay. Now, going further in this topic, I will discuss briefly, like I said, fans and blowers, and also I will talk about liquid cooling system. Okay. So in this case, that's available. So as I mentioned before, if you're doing convection, especially convection and radiation, we should be using the conjugate heat transfer solver in CST. Okay. It doesn't matter if it is natural or forced convection. Any of those are available, and they will. So the CHT solver will solve them with high accuracy. Okay. So the way you go about adding this to your system is basically you can add fans, you can add openings in the simulation domain. Okay, there are certain characteristics on each of these elements. As an example, you can use a fan to define, to prescribe, let's say, a flow property within the same fluid. So as you see here, the computational domain is quite big on this picture. So there is a fan inside of this. And that fan is inside of, so we have two elements. So let's say two boxes separate. We have the background. We also have inside of this element different structure, let's say. And we are prescribing flow properties within the same fluid. So it's only one fluid, which is air in this case, okay? With viscosity, of course, dynamic viscosity to make it a fluid. And if you use a fan, one of the characteristics is that the mass, for example, can be transferred through the fan, okay? You can also use an opening. If you use an opening, normally we use those on the faces of the bounding box, okay? So you can take any of your faces of the bounding box of your system, and use it to introduce certain fluid or certain, in this case, air. Okay, you can do it with velocity, even with a pressure if you want to. That's also possible. Okay, and an interesting thing is that we also have available, actually since this version 2025. We also have available, if you're doing the fan creation, you can do a linear, non-linear, based on a curve for the fan. But we recently added the option to use machine learning, okay, to create that non-linear curve. You only have to introduce a few parameters for the fan, and CST will give you the curve, so flow rate versus pressure of that fan based on data sheets available. Okay, so that's there if you want to use it. Another interesting active cooling option is using what we call fluid domain. Okay, this is only available on the conjugate heat transfer, of course, because we are talking about forced convection in this case. Okay, so if you're doing liquid cooling, you can define that fluid domain. The characteristic of that fluid domain is that it must be closed and it has to be separate from the background. This is very important. Okay, so that fluid cannot touch the background. Let's say background in this case could be air. Okay, and this setup will allow you to simulate a system like a water-cooled pipe or a multi-fluid environment if you want. Okay, so in a simulation like this, we have two fluids actually. We have the water coming into the pipes, and we also have air in the surrounding background. Okay. So the way you go about, or the way you solve the fact that the fluid cannot touch any other fluid in your system is basically you can use lids, okay, or you can use solids. Okay. Yeah, that's very simple. I will show you an example how this works exactly. Okay. Now let's discuss one very important topic that normally we don't pay too much attention, to be honest. But when it comes to boundary conditions in any simulation tool, okay, boundary conditions are very, very important if you want to get accurate simulation results. Okay, and since we are moving from one solution to the other, so let's say if you're using the wizard to create an electromagnetic and thermal simulation project, it might happen that the same boundary conditions, let's say the size in the background is very similar. So the size that we have in the electromagnetic problem will stay in the thermal simulation. So this is something that we need to check and consider, okay? Because an electromagnetic problem might not need to have more or less space compared to a thermal problem. Okay? And this, there are two things that we need to consider. So if we want to understand how large should be our simulation domain. Okay, so are we dealing with a forced convection or are we dealing with a natural convection? Okay. If you're doing forced convection, the domain is usually placed where the physical walls are. So in this particular example, it's just a box. I have an outlet in here for the air to come out, and we have a fan in here, but this is an enclosure system. It's an enclosed system, basically, okay? So basically, our simulation domain should be this box, okay? You can add more space if you want to on top because we have an outlet in here, okay? We should have some space going up in that direction so you have an idea of what's happening with the air, if it is going up or if it is a backward flow of air coming inside of the fan. That's also possible in CST. Okay, but normally if you do forced convection, it's all let's say the boundaries are placed where the physical walls are, basically. Okay, so if you do natural convection, that's a little bit different. And we have a rule of thumb for that, okay? It follows something like this, like the picture that you're seeing here below. So you have to consider the size of your simulation model, the largest size dimension, okay? And then you can add certain distance in the background, okay? Normally for natural convection, we use open added space, or let's say open, not open added space, open, and we increase the size of the background to make it something like this, okay? 2 times up and 1 time down on to the sides, basically, okay? This side does not need to be precise, of course. My recommendation is always to check the temperature and velocity plots and modify the size if needed. Okay. And some, let's say, considerations or practical examples that we can mention is that so you have to ask yourself and I show you here 2 examples. Well, of course, we might have more examples than this. Okay, so 2 examples. Is the PCB situated on a small assembly gig with a low thermal conductivity that will allow the free airflow all around it? So if that's the case, if you're using CHT solver, you should apply open boundary conditions throughout the domain. Okay, exactly as we discussed before with a natural convection, that's the way you go about that. So assign open boundary conditions and consider the size of the element to have an idea what should be the size of that computational domain. Okay, if you're using a classic solver, we normally use a thermal surface property, okay, and surrounded with vacuum. So with the classic solvers, we do not have fluid, so the air surrounding the PCB will not be a fluid. Okay? But we can approximate convection and radiation by using thermal surface properties if that's what you want. Okay? But since in the classic solvers we don't have fluids, okay, there is no need of increasing so drastically as we did before with the natural convection. We don't have to do that with the classic solvers. Okay. By doing certain amount of space, and you should always do a convergency analysis, or let's say accuracy analysis based on that bonding box size. Okay. Now, the second example I have is if you have a PCB that is situated on a flat surface, for example, a big table. Okay. If that's the case, you should consider including part of that table in your model. Okay, and apply appropriate boundary conditions to its outer surface. Okay, you can use either adiabatic or isothermal, depending on the physical scenario. Okay, or you can go further than that and you can remove the table. Okay, and simplify even more the analysis by using directly either adiabatic or an isothermal boundary conditions. Okay. Depending on what you choose, you should check your results, final results, to understand what CST is doing in this case. Okay, because it might happen that if you have very low conductivity, if you use adiabatic, what will happen is that the CST will tend to overestimate the temperature. Okay, and if you use isothermal for surfaces that have high thermal conductivity, this will tend to underestimate the temperature. Okay, so please consider this when you're doing your analysis. You can start with something simple like using directly based on what I'm saying here. You can start by replacing the table and using these boundary conditions. Okay, and for comparison, you can bring the table with the correct material properties, or not the entire table, part of that table. Okay, and run the analysis to understand what exactly is happening. Okay. One thing is that we should consider, if you're using CHT solver, make sure that the surface is assigned a non-slip condition. So if any, let's say, resistance on the surface of the faces will be considered when CST is calculating whatever flow surface interaction we have. Okay. And so that's in theory, that's what we have in the theoretical part. I will switch back now, switch to CST, so I can show you a little bit of what I did, and perhaps show you, we still have some time, perhaps show you how this works in real life. Okay, so let me go to my CST. Give me 1 second. And let me, Manuel, can you tell me if I am sharing? I should be sharing right now CST. Just let me know if you can see that on your screen. Okay. So
yes, I can see it. Thank you.
Perfect. So I have 2 simulation projects in here. Okay. So just to show you how this workflow works. Okay. I have a simulation of a PCB. This is coming directly in PCB Studio. Okay. So I imported this project as an ODB++. And I am doing an IR drop analysis for this PCB Studio, so I get the DC losses and move that to a thermal project. Okay, and I also have another project over here. Okay, this one, in this project, I'm using this one is a very simple project as well. I'm using liquid cooling. Basically, I'm using a fluid to cool down the heat coming from a chip, which is this one here at the bottom. Okay, so let me start with the PCB. So as I mentioned before, so if you're doing DC losses, you should be using IR drop in this case. The way you go about activating that, go to the next window, is basically you have to go to the setup of the solver, okay, in specials, and in there, under co-simulation, you will have this export losses for thermal solver. That's the only thing that you have to do, okay, when it comes to moving the losses to a thermal simulation. But keep in mind that you have to, because if you're doing IR drop, that means you already prepare your components nets for that particular analysis, okay? So keep that in mind. You should have already created either voltage sources, voltage regulators, current sinks, all of that should be there. So CST will recognize what are the components involved on that IR drop. Okay. So once you do that, you can just solve the problem, just start the analysis. I already have the results in here, and you will get this 0D results to the 3D results. Okay. This let me just show you the results. Okay, let me bring surface currents. I will deactivate this. And let me do a log scale on this one. Perhaps power density will be easier. So just to show you, to give you an idea what you get, something like this. So you get something, in this case, my nets, the nets that are involved are actually, so over here, and some of the elements are over here. So I have components in all of these places and nets involved in all of these places. Okay. So the losses, power loss density will move to the thermal project as a field source, as you will see now. And you also get a 0D result, which will show you a list. So something like this will come up. So the results that you see here is part of the typical IR drop analysis, okay? But what is important for us is power losses on the components. So these losses in the components will move to the thermal problem as a heat source, okay? So that's basically what we need to do on PCB Studio. So once you have that, let me close this, then we have to move to the schematic, okay? And I already have a few of these projects created in here. Okay? So the only thing that you have to do is create a simulation project directly in here. That simulation project should be of thermal and mechanics. So these are the modules available in CST, okay? Should be a thermal mechanical problem, and from here you can select the solver that you want to use. On all of these examples, I'm using the conjugate heat transfer. Okay. Once you do this, the only thing you have to do is click OK, and it will create a project something like this. So a project like this one, Of course, I already modified my bounding box because initially it will not come on with this size. So I'm talking about the big blocks I'm showing here. Okay. So it will come something like this. And this project has no simplifications, as you can see here. Okay. And as I mentioned, you will have a field source coming directly from, and actually let's go inside of that. So coming directly from the IR drop analysis. That's why it's a source field coming from here. And you also get the heat sources for every component involved on this analysis. So the heat sources will come with certain amount of watts of power. Okay, that's the way it works. From here, the only thing that you have to, well, not the only thing, you have to worry about that few things. You should check your background. Okay, in this case is natural convection. That's why I have certain amount of space up, down, and the boundary conditions are open, as I mentioned before. In this particular case, I have no symmetry, so that's there. And of course, you have to check what the solver setup. You have to check that, activate if you want to analyze radiation, if you want to analyze convection using fluid, or air in this case as a fluid with certain gravity. That's also there. Okay. And if you want to do acceleration, hardware acceleration, you can activate that directly from here and just start the analysis. Okay. Again, as I mentioned, this project has no simplification whatsoever. So it comes directly like that. And of course, you have to worry about the mesh as well. I will not discuss too much about the mesh today, but you have to worry about how the mesh looks like. We will talk about that in the liquid cooling in a moment. Okay. For comparison, I did the same analysis, but using a simplified model. So this model, instead of having, so in the previous model, I have my vias, I have all the traces. It's not like that. It's not like that in this one. I have simplified that using layer wise. And for each layer, it's basically an average of whatever you have on that particular layer. Okay. And I run the simulation, both cases. Of course, if you use layer wise, you can see the mesh count here at the bottom. This one, layer wise, will be lower that without simplification. So we have almost 3 million in here without simplifications, and we have like close to 1 million. So there is a lot of reduction in mesh count, and of course in simulation time. Okay. So if we compare the results, you will see. Let me just bring the temperature, and I will create a field on a plane, just to give you an idea the way it looks. Let's activate temperature on this one as well. And for comparison, you will notice that there is no much difference when you use layer-wise or when we use no simplification. Okay, so there is a difference. There is a 1 degree difference there. Okay, but in terms of getting fast simulation results, I think you can use layer-wise initially. Okay, and if you want to, you can move to a no simplification problem and analyze what's happening. So you see 89.8 degrees for a no simplification project, and when you use layer-wise, you get something like 88.9. Okay. Of course, the way the heat travels in the structure, if that's important, you might need to consider a no simplifications, or perhaps a no simplification on certain area with area restriction, and layer-wise everywhere else. Okay. So that's for this part. I run the same project now. I have another project prepared here, but in this case, I'm using a fan. Okay. I created a fan. It's very simple to create a fan. You can use the toolbox, as I mentioned before. The toolbox will, let's say I'm using the actual fan actually in this one. So you only have to introduce physical dimensions of that. And this one is working with my axis, my coordinate system, which is here. When you see the Z, X, Y in black, I can activate I can create my own working coordinate system to change this. create the fan wherever I want, basically. Okay, so that's the way I created the fan. It's very simple. I just extrude some of these elements, so to make it bigger in the X direction. That's it. And I added this outlet for the air to go out from this structure. Okay, and you see I'm not adding any element to the sides in here, and that's why because I'm using a boundary condition as adiabatic. Okay, you can you can close this completely if you want to. It's not a problem. Just for simplification, I'm using adiabatic and I'm using open on this direction, so the air can flow over here freely, and open on this direction, so the air can enter the structure. Okay, and yeah, the background is like this. I'm not using open or with extra background on this particular case. This is forced convection, as we mentioned before. And of course, I will have my heat sources. I will have my field source also there. The way you create a fan, for that, you just have to select the faces. Let me just bring the fan over here so you can see it. I already have my fan here. The way you create a fan is selecting faces. So when you activate this, CST will ask you to select an entry face and an exit face, basically. That's why I have two elements, one in blue and one in red. So that's my entry, and this is my exit face. That's it. That's the only thing that you have to do. And of course, you will get this window saying what are the properties of this fan. Okay. In this particular case, I'm keeping the ambient temperature, which is 20 degrees. You can add dissipated heat if you want to that. And I'm using that machine learning capability that I mentioned before. I just have to introduce frame size, which is based on the actual size of the fan, rotation speed, and the flow pressure characteristic that I want. And CST will create a curve like this one that you see here. And whatever altitude consideration that we need to have in here will automatically be considered on this curve. Okay, unless you deactivate that on the setup of the solver. So that's the way I did that. Of course, this will be forced convection with a fan. If you check the results at the end, you will notice that, for example, let's see temperature. Before we had like 88, 89 degrees Celsius on one of the chips, basically, which is here, this one at the bottom. Just by using the fan, we reduce that to 57 degrees Celsius. Okay. And there are other options here for visualization. You can also visualize velocity, which also apply to fluids. So velocity plots will allow you to understand how that. Let me change this to streamline so you see a short animation of this. So you can bring something like this. Okay, just to have an idea. This one is very simple model, but it might be more complex than that. Just to understand how the air is traveling inside of the structure and it's going down. Okay, and the velocity on this, you can also check the pressure and the viscosity on this outlets in here. Okay, so that's if you want to use a fan. I also have another project in this particular case, and I will close this so I don't have it in the middle. I have a very simple model with a chip with a heat source applied to that chip. I will show you that in a moment. So I have a chip with a heat source applied to that with a very high power applied to that chip, considering the size of the elements I have here. Okay. Again, the background. This is natural convection, although we have fluid to cool that, but this is natural convection because it's sitting in there. Okay, that's why I need so much space. And the way you go about to creating that fluid, first it have to be enclosed. So You have to be close, and you have to be in a model completely close and separate from the background. As you see, the fluid is going in here, the background is surrounding that fluid. So we have to separate that either with a solid or with a lead. In this case, I use a lead. So let me show you my fluid domain. It looks something like this. The way you go about creating a fluid is basically you just click on fluid domain and you have to select an inner face. Okay. If you see here, I'm selecting the inner face of this tube. So this tube goes all the way inside of my simulation model. And that's the only thing that you have to create. Okay, CST understands if the faces are connected and close, so there is no gap between the faces, this will work perfectly fine. The arrow should point inside of the fluid. Okay, that's very important. So that's one thing. Since the background is over here, so our open condition is over here, and we have air surrounding that, we have to separate that. So I use a lead. To create a lead, I first create this sheet. It's a simple sheet, no thickness applied to that. In this case, I've used copper for that sheet. It doesn't have to be copper. You can use any other material. It's not important in this case for the simulation. Okay? And then you create leads by selecting those sheets. The arrow also is very important. The arrow should point inside of the structure, of the fluid, sorry. Okay? Where the fluid is, into the fluid. And for that, once you do this, you can prescribe certain, let's say, flow rate in this case, or you can use velocity or pressure if you want. Once you have this, of course, you need to check the mesh. Let me just do it very quickly in here. If you have a fluid, there is a lot of interaction between the fluid and the surface of the elements in there. And since you have a very well-designed cooling system, you will have a lot of heat coming up from this aluminum. Okay, so that's why I have this mesh created in here. The way I go about that is, in this particular case, I use local mesh refinement. Sorry. Where's mesh group? Sorry. I use local mesh refinement on my fluid. So I have a dummy object. I didn't show that part, but I can show you that very quickly. I have a dummy object inside of this. Okay, that dummy object is part of the simulation. So it's part of the bounding box. So it's mesh, but it's not part of the simulation. I have excluded that component. Okay, so I have a dummy object, and I basically tell CST, well, I want to do a local mesh properties on that near to the model. Okay, and also extend that which is near to the model. That's why I get so dense mesh in the proximity of that. So once you have that, you can run the simulation model, and with that you can obtain something like this. I will create a cut plane so I can show you something like this. Okay, so the air is also a fluid in here, and let me create a cut on the Z plane so you have visibility of what is happening inside of this. Okay, so you have something like this. What you're seeing is the temperature plot with the fluid inside. If you're not sure, you can also activate the velocity plot to understand how the fluid moves inside of this, of the cavity. Okay, and we also have the option to get pressure. There will be a pump, a water pump in this case, pressuring water in here, but you can also activate that in case you have to improve the design of that water pump. Okay, so with that, I think I got to the end of the presentation. Let me switch back to my presentation here. And with that, I end my presentation, today's session, and I think we are open for Q&A. We still have a few minutes if we have questions available on the chat.
So thank you so much, Daniel. So I think we have one question here, which is, when working on PCB cooling simulation, what key settings or parameters should we focus to ensure accurate results?
Okay. So there are a few of them. I would say first check the PCB layout. Okay, how much accuracy do you want to put on that 3D model? Do you want to add simplification or not? I would suggest adding certain amount of simplification and keep it without simplification on the important parts. Okay, where you already have a heat source created. Okay, just to understand what is happening inside of those many layers and inside of the estacado. That's one thing. The other thing is check your material properties. I briefly mentioned that, I think, but if you're doing radiation, for example, you should consider emissivity. So make sure you have emissivity properties assigned to that material. Okay. If you're doing convection, make sure that you have dynamic viscosity, for example, assigned to that material properties. Otherwise, CST will not take these parameters and use that to calculate the heat, that form of heat transfer. Okay, that's another thing. The next one is background size and boundary conditions. That's very important. Okay, consider the examples I mentioned here. So if you do natural convection, so leave certain amount of space. If you do forced convection, consider simplifying perhaps the model by using either adiabatic or isothermal boundary conditions. Okay, and the last one will be the mesh. Okay, always check your mesh. The initial mesh that CST creates works for many applications, but when it comes to, if you have a fluid, let's say you have active cooling, you should consider improving the mesh close to where you have fluid surface interaction. Okay, and close where you have that interaction between surface and background. Okay, and yeah, that's basically what I have. I hope that answered the question.
All right, thank you so much, Daniel. I think that's the only question we have now so far. So with that, I think that brings us to the end of the session. Thank you again, Daniel, for this great presentation, and thank everyone who joined us today. We hope you found this session really valuable and informative. So thanks again, and I hope you have a great day.
Thank you, everyone. Thank you for joining. Have an excellent day.